Ronceray. Sorry, my French is worse than my Portuguese. So Pierre he got his PhD in Paris, and then he was a postdoc in Princeton for 5 years, more or less.
Ish.
And now he's a group leader in Marseille, in the Century Center, and he's also a CNRS researcher. He will be visiting until the 18th, so if you want to talk to him, you have still some time. And he will be talking about inference from stochastic trajectories.
So, hi everybody. This is a small audience, so I mean, feel free to ask questions and interrupt. And the goal is that everybody is on board, and it can be kept relatively informal. So one of the main goals of my research group is to try to discover models from data. And so we're a biophysics research group in a mixed experiment and theory environment. And I'd like to start with giving you a very broad view of how, in my opinion, we advance the study of the dynamics of living systems. So the dynamics of living systems, meaning how biological stuff moves and evolves in time, from the scale of single proteins inside a cell to the scale of cells moving around, collections of cells organizing, up to the scale of groups of organisms, such as birds, exhibiting collective dynamics. This is the subject of very intense research on many different levels, there's still a lot to discover there. And how do we do that? How do we connect this real-life dynamics of biological systems, of proteins, cells, and organisms, with the pretty abstract theories that are developed by theoretical physicists, such as active matter theories, active gel theories, criticality, concepts of non-equilibrium thermodynamics, etc. So there's quite a large gap, because you do not get a theory just by looking at these systems. And on the theoretical side, which is where I come from, what we've always been doing is modeling, meaning that we instantiate the theories by defining equations that we think model well, represent well the living systems we're studying. This can be in an Ising model for a magnet, a Vitschek model for a group of birds, etc., etc. But there's still a large gap between this and the actual experimental data. So on the other hand, what experimentalists have been doing for a few centuries is imaging, looking at pointing microscopes towards the biological matter and getting images, or in the case of studying the dynamics, getting movies. But these movies are qualitative objects that you can look at, but do not directly connect to models. To get closer to models, what people do is track the objects that are present in the movies. So track the bacteria, track the individual molecules using super resolution techniques. And the outcome of that is trajectories, meaning space-time traces of the objects that you see in the movie. So but then there's a last gap, which is between trajectories, so these raw data, and the models that we want to connect them to. And that last gap is called inference, connecting models to data. And this is the goal of my group and the goal of this talk. And I'd like to emphasize the fact that there's been, in the past 2 decades, tremendous advances in imaging. The discovery, basically, of super resolution microscopy, which won a Nobel Prize more than a decade ago. That's been the start of a flurry of new methods of microscopy. Maybe more discreetly, there's been a lot of progress in tracking in the past, not even 10 years, more like 5 years, due a lot to the advent of deep neural nets that are able to pick up information in images where algorithms before that were unable to identify objects. And for instance, the discovery of U-nets, which are segmentation algorithms, which can recognize the shape of cells and then track them dynamically along a movie, has been extremely instrumental towards getting lots of trajectories. So these trajectories are abundant nowadays, but the inference methods to connect them to data remain weak, and I'll explain you why. So the main player then is these trajectories. And the question is, how do we infer dynamical models from these trajectories? So what do I mean by trajectories? Well, you might have in mind the classical trajectories, the orbits of planets, for instance, that are described by typically ordinary differential equations that, such as Newton's laws, that predict deterministically the evolution of the system. However, if you run the same experiment with the same initial conditions twice from biological data, you're very unlikely to get the same results. So the outcome of the trajectories are not going to follow a deterministic law. Rather, they're non-deterministic due to different sources of stochasticity. On the very small scale on the molecular scale, thermal noise is an intrinsic source of randomness. So the bumps of the random bumps of solvent molecules on proteins, large macromolecules, etc., are intrinsically random. If you look at a slightly larger scale of large cellular structures up to the cellular membranes, the cell nucleus, etc., then the thermal noise becomes less and less relevant. It's because the larger the object, the lower the relative importance of the thermal noise. But the active fluctuations coming from all the enzymatic processes, all the molecular motors acting and exerting forces inside cells, start building up and shake the inside of the cell like a giant pogo, and result in another layer of randomness. And even that goes down in importance if you go to larger scale of full cells, small organisms like C. elegans, all the way to groups of large organisms, where really there's no deep randomness in their motion. The bird knows where it wants to go, and it controls its dynamics to go there. But there's, from the point of view of the observer at these levels, there's an emergent noise that comes from the inner complexity of these objects. You do not know everything that the bird has going on in its brain, and to model this ignorance, you use stochastic dynamics. So at all these levels, rather than using ordinary differential equations, we need to use stochastic models, non-deterministic models, in particular stochastic differential equations. So the most simple one is just an extension. Sorry, the most fundamental one is just an expansion of Newton's second law, which is just adding a random term here that is time uncorrelated, and that models this coupling to these random events. But since we're interested mostly in small-scale systems, such as cells and intracellular processes, the inertia in these systems is completely negligible. So this acceleration term can be omitted, and that results in overdamped dynamics, and that is to say Brownian dynamics. So that Brownian dynamics, if we have a closer look at it, it results in these familiar random fractal-like objects, where on very short time you have fast random interactions that dominate, and that we model as Gaussian white noise. But on the long time, there can be emergent structure due to slow deterministic trends that we will model as forces, or rather as drifts. So mathematically, what the type of systems we're looking at is this type of stochastic differential equation of order 1, dx over dt, where x is a quantification of the state of your system, so the position and orientation and possibly shape of one or many particles, cells, bacteria, birds, dx over dt equals a deterministic term that evolves slowly in time, and that is a function of, it's a vector field function of the state of the system, plus a random term that is quantified by a diffusion coefficient or a diffusion tensor if you have anisotropy in a system, that is also possibly a function of the state of the system, times a random white noise, psi of t. So to be precise, when I see an equation like that, what I want to know is how to simulate it. So the way to simulate this equation is for a small delta t to increment the position like Euler's method. So delta x over, so x of t plus delta t is the increment, so x of t plus f, the force, times delta t. So that guy is basically the Euler method. It's the usual integration of a differential equation, plus a random term that scales as the square root of delta t, but that has an amplitude that is a random variable, such that the law of large number results in this Gaussian, this Gaussian behavior. And so that part is dominating at short times because it scales as square root delta t, which is much larger than delta t for small delta t, but it's fluctuating. So if you integrate this algorithm, which is called the Euler-Maruyama algorithm, you will get Brownian dynamics. And that's just one example of stochastic differential equation. There's many extensions to this, for such as underdamped dynamics, where you restore the inertial term, the acceleration, colored noise or non-Gaussian noise. You can be externally driven. So here it's autonomous because the force and the diffusion are only functions of the instantaneous state of the system. It can be no-Markovian, meaning having memory effects that depend on the past of the system, etc., etc. The question I'm asking is, how do we learn such dynamics from data? And at this stage, I would like to know if there's any questions on if all of this is clear. Should I keep going?
Not that a physicist would help this, but you just have some
Yes.
distribution of velocities, and you say, look, I just want to map the distribution of velocities for some reason.
Okay, it's not velocities. It's the mathematically exact term is drift. It's not a velocity because the velocity is dx over dt, and x of t is not differentiable. So the velocity is not defined. But it's the average displacement averaged in the right way. Dx over dt is, well, is what we would call the velocity, right? But here it's infinite all the time, because that Gaussian right noise is made of delta peaks. So if you look at this, this trajectory, it's non-differentiable. And only its average term is differentiable. Things don't move in jumps, but if you look at the trajectory of a colloidal particle, for instance, that's a micron, and you observe it at the time scale of millisecond, for instance, which is what a microscope can do, you will see this. And the continuous inertial dynamics that is continuous, you would need 6 orders of magnitude more of time resolution to see it. Yes, but 6 orders of magnitude is a bit more than an increment. It's, I mean, fundamentally a different mathematical object that can be used to.
Living things jump, they don't move continuously, is that right?
This is continuous. It's non-differentiable. It's the...
So living things obey non-differentiable trajectories, is that?
Yes.
And non-living things don't?
Non-living things do too. At this, yeah.
If you throw a stone, it has a non-differentiable trajectory?
If it's a very small stone, you will see that it's and it's in a solvent, you will see that it's non-differentiable. Yes. Do we have example? Let me.
Solvent? I guess air is not a solvent.
Air is a solvent. It's
You say if I throw a stone, I should think of it as a non-differential trajectory.
if
I think, that is a mathematical tool, no? It's just because the white noise, it's uncorrelated, and that's for convenience. Usually you need to consider that the white noise has a finite time correlation.
okay, so these are experimental trajectories of colloidal particles. These are viruses. These are cilia that you look at, so the long, straight molecules that bend. If you looked at it with an infinitely powerful microscope at an infinite frequency, you would recover Newton's laws and see that it's continuous in time. Well, not going to further fundamental problems, let's say. But
I just don't understand why it's useful in physics to think that things are continuously differential, but a live system somehow it's not.
okay, Brownian dynamics is not exclusively used for living systems. It's actually an extremely broadly used.
Okay, so you're just saying they're very small, is that right?
Not just very small. Basically, it's a question of the relative importance of these two terms. That type of equation is extremely important, for instance, in finance, where this term models the individual behavior of actors, and this term is the global trend of the market. It's very useful in neuroscience to model the brain dynamics. This is the shot noise of individual neurons. This is the global trend of the global dynamic law, etc., etc.
You're saying that there's randomness, then you don't know away from that. Okay.
Randomness is ignorance. So the
So I use randomness.
ignorance of parameters that interact with the systems, but that you don't monitor. For instance, you don't know what are the positions and velocities of all water molecules in your glass of water. And so we model it as random terms.
What I'm trying to say is if psi plays a useful role, then you have to have something to do.
Yes.
I think that's
And it's a model. It's non-fundamental. It will break down if you look at it too closely, but it can be very useful on several orders of magnitudes of length and time, and so it's important to learn it. More questions? So moving on, hopefully you're motivated to still look at this type of dynamics. So the question is, how do we learn it? So basically the problem is starting from an experimental trajectory. So the track, for instance, this is the track of an individual cell. So you have a time series of positions or orientations of one or many particles. And what you want to do is reconstruct a model within this class of stochastic differential equations, meaning learning the force and the diffusion fields that are functions of x and of x. So to do that, there's a common approach, I would say, which is to fit what the so-called Kramers-Moyal coefficients. So the Kramers-Moyal coefficients are just the first and second moment of the time increments of the dynamics. So if you look at a single time step, delta x equals f delta t plus square root 2d times random variable times square root delta t, then you can actually separate the two contributions, provided that delta t is small enough. Indeed, because this term has zero average, if you take the average of delta x over delta t, so the ensemble average, when delta t goes to 0, you get the force or the drift. Similarly, if you take the average of the square of delta x, then you can extract this term, which is dominant when delta t goes to 0, but random, and that will give you an estimator for the diffusion tensor. So this is a nice method that has the advantage of being very simple. That gives you quantities that average to these two fields, and you can basically perform a basic inference by just doing a grid binning. You separate your process on a grid. You take all the data points that are in a grid square. You average these two quantities, and that gives you F and D locally averaged. This is a very rudimentary approach. You can do more sophisticated stuff, like a linear regression that fits this with continuous functions, such as polynomials. And that's basically the state of the art of stochastic inference. It works generally with some caveats. Before explaining.
Sorry, you probably said where delta t is a half constant, but if I look at the above equation, I just multiply both sides by dt, I don't see a delta t. The equation above.
This one?
The top equation, inferred model.
Yes.
If I just multiply both sides of the equation by dt,
Yes.
it looks like there's no delta t to the half. Where did the delta t to the half
So
come
that's, it's this psi here.
from? Xi is in the square root or some, I don't know.
This xi is a Gaussian white noise, meaning a random process that obeys xi of t prime equals delta of t minus t prime, where delta is a Dirac function. So if t is different from t prime, it has zero average. That's total. It's time uncorrelated, and at equal times, it's a delta.
May I add something about the velocity distribution? Because I didn't catch exactly the question. Was it about velocity distribution?
It was about the definition of velocity and the fact
definition. Okay. So just to remark that velocity, instantaneous velocity is not defined, but you can define the distribution and in general, and the moments of the distribution of velocity, also the instantaneous velocity is not. So not just the average, but under wide assumption, all the moments.
Yes, basically, if you look at the time increment so this is delta x over time delta t, and you look at the probability of delta x, what you will get is a Gaussian, because we are approximating a Gaussian process that is centered around f delta t, and that has width that's going to be a square root 2d delta t. Yes. And so the width is much larger than the average. So when delta t goes to 0, the relative signal to noise goes to 0. This gets to 0 much faster than the average, than the width goes to 0. Yes?
Can you elaborate a little bit about the more sophisticated linear regression method that you...
Sure. Because I'm going to explain why they're bad, I should explain what they do first. So basically, what you're doing here with grid binning is fitting your force on your diffusion fields with a function that is constant in each of these squares. So it's a constant by parts square fit. But you can fit with better functions than that. For instance, you can, so basically you can fit with any parametric function by trying to minimize the least square distance between your fitted function and the actual Kramers-Moyal signal. So
You mean you have some form for the f of x in terms of some functions?
Yes.
For
So typically, if you try to fit f hat of x, which is the inferred force field, as, for instance, a linear combination of known functions, a sum over, let's call it alpha, just of f hat alpha b alpha of x. So these are the fit functions. Then you can get these fit coefficients by minimizing the least square difference with delta x over delta t. So you can write that f hat alpha is the argmin over the f alpha of f hat of x minus delta x over delta t, all of this squared time averaged. So you minimize the distance between your fit functions and your... Okay, I'm actually going to skip this next slide to move on directly to why this does not work very well. So the reason why... so this is a nice approach, this and grid binning, and it works very well for mathematically perfect signals. What do I mean by mathematically perfect signals? I mean a time series which goes on infinitely, which has an infinitesimal delta t, and which is perfectly resolved. But the problem is that, and for instance, the most cited method that provides such, the most cited paper that provides such a method uses, benchmarks the method with trajectories that have tens of millions of points, with thousands of points per period of the system, per typical time scale of the system. This is not what you actually get typically with biological data. Why? Because the typical trajectories that you get in experimentally, first they're short. The real trajectories are short because individual fluorescent proteins will bleach out and stop being fluorescent after emitting a number of photons. Cells just die out. Birds fly away. Then they're also sparse. There's a finite delta t, and so you don't know what happens between consecutive points. There's just uncertainty here. They're noisy. You don't get an exact representation of the system at every time point. Actually, there's a measurement error that is induced by the measurement device and by the tracking algorithms. And last but not least, they're partial. You never observe the whole complete set of degrees of freedom that characterize the system. There's always something that is out of field, out of focus, too dim to resolve, or just hidden and that you don't take into account. And so what you get is what your system really is a high-dimensional continuous dynamical system. But all you have to infer this high-dimensional continuous dynamics is this low-dimensional imperfect signal that is short, sparse, and noisy. So how do you do that? Well, that's much harder. To do that, what we need is methods that are data efficient, meaning that are able to extract efficiently the information and get the parameters of the models, and that are robust, meaning that are not affected by the imperfections of sparsity, of noise, and to some extent of partial observations. So this is the goal of my research. I'm not going to focus too much here on the partial part. That's kind of a future research direction, and just say a little bit about sparsity. But here I'm mostly going to focus on trajectories that are short and that are noisy. How am I doing with time? Yes, I'm going to skip this part. Okay, so why are this type of approaches not good with imperfect data? Well, there's a fundamental reason for that, which is that if you solve this minimization problem, what you get is that the optimal inferred parameters are the time averaged delta x over delta t times b beta of x. And then you need a normalization that I'm going to write as this inverse covariance matrix, C minus 1 alpha beta, where C alpha beta is the average. So this is the time average. C alpha beta is B alpha of x of t, B beta of x of t. So basically, this is a normalization matrix, and this solves the least square, this least square problem. So this is the maximum likelihood, if you want, estimator for these F alphas. But there's a big problem with that, which is that it's a maximum likelihood estimator in the case of perfect data. But if you have a little bit of noise, so this delta x here is x of t plus delta t minus x of t. And if you have a bit of noise on this x of t, it's going to correlate with the noise on this x of t. And that's going to result in biases of order 1 over delta t.
Sorry, now I got confused about the B's. The B's are non-functions, aren't they?
The B's are non-functions, yes.
And what do you mean by a noise in B?
It's not a noise in B, it's a noise in the argument of B. So if x is the exact x plus some random noise that is induced by the measurement device, then this random noise is amplified by basically the differentiation of this quantity, and so results in a large bias of order, I can write it as the mean squared error, the mean squared measurement error divided by delta t. This is a dangerous bias, because if delta t is large, well, you don't see anything because your force changes over time. If delta t is small, this diverges, and you don't have any signal. So that's the bad guy that I've been fighting. And to do that, I've proposed an alternative method, which we call stochastic force inference. And that's a collaboration with Anna Frischmann, who's a professor at Technion, which basically is very similar to what I wrote here. It's least square fitting with smooth state-dependent functions B of x, for which I use a maximum likelihood estimator that I modify using a stochastic calculus correspondence that is called the Ito to Stratonovich correspondence. So basically, it has all the advantages of this pre-existing method. It's provably convergent, it's efficient, it has the flexibility of providing good representation, but this extra insight protects it against experimental noise. So in practice, how does it work? Well, we do just as we would have done here, so selecting fitting functions. Our input is the time series. We select the fitting function. So for that, the more insight you have on the structure of your system, the easier the problem is. If you don't know anything about your system, you can use, for instance, polynomials. That is a family of functions that can represent anything, but converges slowly. Or you can use Fourier modes. But if you know exactly what the functional form of your system is, then put this information here, and it will facilitate the problem. Then you compute these force-fitting coefficients. So these F alphas using this modified maximum likelihood method And the reason, so this is the formula, so it's basically the same, a time average, a normalization, this delta x over delta t times, now b, this function b is applied as, not as xt, but as x t plus delta t over 2. So not as the initial point, but as the midpoint. And the reason for that is that the measurement bias that came from the correlation between xt in the fit function and in the delta x over delta t is cancelled by another measurement bias with a different sign coming from the t plus delta t term. There's a price for that, which is that you need to, that you've pushed everything in this d grad b term. So that means two things. It means that this gradient, that this b function, this fit function should be differentiable. So you can no longer use this grid binning because these are non-differentiable functions. And you need to have an estimator for the diffusion coefficient. But that is actually a much easier problem. So that's why it works. You can estimate the error. We have estimators for the error that are self-consistent, meaning you don't need to know the ground truth to know whether your results are consistent. And so the error is basically the square root of the number of fit parameters divided by twice what I call the information present in a trajectory. And that information is the average, average square of these fit coefficients divided by the diffusion coefficient. And it's linear in time. So basically, the longer your trajectory, the more information you have, and the smaller your error, or the more parameters you can learn at a given error level. So this is complemented by feedback loop that allows you to adjust the number of functions to minimize this relative error. Basically, there's a principle which is the maximum information principle that allows you to select the sweet spot where adding a few functions would lead to a bit less good results because of overfitting, but removing a few functions would lead to a bit worse results due to underfitting, due to a default of representation. So all of this is self-consistent, and so the output is a force field, a drift field that is inferred. We also have the same for the diffusion field with a controlled accuracy. So it's all on GitHub, and you're welcome to try it if you have data that you think it might be interesting on. We've been doing a lot of benchmarking, so we can prove that it's data efficient compared to, for instance, grid binning. So you see that, so this is the inference error as a function of the total time of the trajectory. So both for binning in blue and for our method in orange, the error goes to 0 when the total time goes to infinity. But here it goes much faster because it represents much more efficiently the data. It's also robust to experimental noise. So if you crank up the measurement noise to model the finite resolution of your system, then, so for instance, I'm adding a small point spread function on this trajectory. So here we had a 5% error with stochastic force inference. We still have a 5% error with stochastic force inference at this noise level, while usual methods such as this one have already broken down. And it's only when you crank up the noise to pretty crazy levels where the noise is at the same scale of the typical length scales of the force field that you lose signal. So basically, this is a high resolution method. It also does very well. Okay, not very well. It's improving on the sparsity, meaning on having larger and larger delta t's. So with typical data parameters, it goes. You need 4 times less data points than usual methods. So here, for instance, to have with these two trajectories, you have 1% error, but this one is with SFI and has 4 times less data points, so the time intervals are much larger. So all in all, it's data efficient and it's robust to imperfections. I'll finish flexing by showing that it works not just for simple low-dimensional systems, but also in higher dimensions, provided that you have some structure in your system. For instance, if you have many active colloids, so many particles that are moving around and self-propelling, this would be a very hard problem to solve. So these particles are self-propelling, the dynamics is very noisy, and Nathan, you can see that it's pretty discontinuous, pretty non-differentiable in velocity. This is a very high-dimensional system, but you can treat it by and avoid the curse of dimensionality by using the structure of it, in particular the fact that your particles are non-distinguishable. And so if you use basis functions that are invariant under the exchange of two particles, so that know about the position of all particles, but not about their identities, then you can actually get a pretty accurate representation of the force field. So to give you an example, with a video of 10,000 frames, so the same video that I was showing, but running for 5 minutes, I can get 99.6% accurate estimate of the forces. So that gets everything. That gets the self-propulsion, that gets the interactions between them, the repulsion, the alignment terms. That's with 10,000 frames, but sometimes you don't have that much. Sometimes you have 25 frames, 1 second of the previous movie, and here you still have better than 90% of accuracy. So the video I showed is a model for this, which is particles that are, these are colloidal particles. They're about 2 microns in diameter. They're made of 2 different metals. And so when you put an alternating electric field, that induces electrophoretic self-propulsion in them. And so they have this kind of dynamics. This is a strongly driven regime.
And you claim that the previous animation represents this?
It's in a slightly different regime, yes.
Doesn't look at all like it,
Yes. Because the experimentalists you like to crank up the activity and make them strongly self-propelled, while I focused on the previous slide on the harder problem. This is much easier. The mathematics of the problems is the same. This is just much lower noise. So this is still exploratory.
Yeah, this case seems to just be in a limit where it's underdamped, no? Or I always mix the words, but basically in a limit where the noise has a finite time correlation. So it's smoother.
No, they're not at all underdamped. They're strongly self-propelled.
Okay.
So it means that they're Brownian, but they go much faster than the typical Brownian time. What is strongly Brownian here is their orientations, which is fluctuating. I should find a better movie than this for this example. So using this technique, these collaborators have been able to infer force fields and torque fields, meaning how these particles align and self-propel. In the future, I want to use this type of methods on more biological systems, and I'm currently trying it on schools of fish that are aligning and self-propelling.
I understand that you want to apply to living systems, but it sounds like it's actually just physical mechanics with no way to something I'm missing.
Yes, it's statistical mechanics that I apply to living systems.
Right, but if you want to test your thing, there's no need to do it with living systems.
it's, okay, because it's harder, okay. The quantification of the dynamics of living systems is the end goal. And it's why I require the development of these methods. And in particular, that's why I require them to be so robust to measurement noise and to sparse observations. So dead systems are much easier to observe. They're also slightly more boring in that there's less at stake and less enthusiasm from the scientific community, I would say, in identifying their dynamical laws.
I'm missing something, but it sounds to me you're just trying to define a nice description of statistical systems and noise. Am I missing something?
So this is already defined. I'm not creating this definition. I'm trying to capture the models, meaning the class of models exists, and I'm trying to identify models within this class.
I just don't understand why it has anything to do with living systems.
Living systems is what I want to apply it to.
Then I understand, but to test your description, so once you've shown that your description is more accurate than other descriptions, then of course you can apply it to anything you
Yes.
want. But it sounds like it's much more work to try to first do it with living systems.
Well, and for that is absolutely true. And for this reason, I do not first test it on living systems. I actually first test it on simulated data, for which I know the ground truth, and then I test it on this kind of non-living systems, which are sufficiently simple and well controlled, but for which there's still interesting questions, meaning that we don't actually know from first principles these laws because of out-of-equilibrium physics. And at the same time, I'm refining these techniques on first attempts on biological systems.
Sorry, I'm not in the field as everybody else. So X doesn't have to be position, right? It can be any parameter.
Yes. It can be the price of your shares on the stock market. It can be the strength of El Nino month by month.
So the interactions have nothing to do with spatial interactions. They're just some parameters in your system.
Yes, I'm interested in. Okay, so my personal interest is in spatial dynamics. And for this reason, I make the method as robust as I can against typical imperfections of spatial dynamics, meaning the ones induced by a microscope, which is, I think, what distinguishes me from the many people who do that in applied math and try to optimize this method for instance, finance. As you can guess, there's quite a bit of money in that. More questions? So we've been doing that with this overdamped Brownian dynamics. There's many extensions that are used in the description of biological systems, and so that and for which we use the insights that we've developed for Brownian dynamics to develop expansions of these techniques. For instance, for underdamped systems, which are second-order differential equations, such as this model for a flock of birds that goes in 3D and aligns and self-propels. One key difficulty in this type of problems is that now the force and the diffusion depend on the velocity, as well as they depend on the position. For instance, in this force field, there's all the friction forces that are included. But this velocity is not directly observed. You only you obtain an estimation of the velocity by taking the difference in positions between two frames. And that induces actually very nasty correlations that result in pretty ugly-looking correction terms in the inference methods that we've worked out with David Bruckner and Chase Brothers in this paper. And once we work it all out, we can infer a model. So basically from these initial trajectories, the green ones, I learn the interactions, I learn the self-propulsion, I then get an inferred model. I check that the relative error looks good. Yes, it looks self-consistent. Then I can simulate it again. So starting with the same initial condition in red, I can run a simulation with this learned model, not knowing what we had done before. And it looks basically the same. It's a collective motion that remains coherent, does random turn, and keeps flocking. So at this stage, we're satisfied that we have a method that infers that kind of underdamped equation from data. More recently, we've been looking at doing the same with statistical field theories. So where now the variables that are observed in time are not a finite dimensional vector, but a continuous field, such as, for instance, the position of a membrane, which is height as a function of x and y, or the concentration of a chemical inside a cell, or the shape of a filament of a cell. And that's the PhD subject of Andonis, who's in my group. And he's found a method to adapt these to infer adapt the inference methods to infer not just the interactions and the nonlinear coefficients in the field dynamics, but also differential operators that depend on the gradients and on multi-point functions of this. So it's still preliminary, but Andonis is working this out. So basically, we have a set of methods that can reconstruct differential equations from stochastic differential equations and their variance from data. We have a small but growing community of users that are starting to use this for cell migration, cellular cell interactions. So this is in these two groups work on experimental biological data in dead matter, such as active particles or colloids, or passive colloids, but also in other fields, such as dust particles in plasmas that represent, that show underdamped dynamics. To give just one quick example before I have to wrap up, David Bruckner, who's a postdoc at IST Austria, works on the trajectory of single cells that are confined in a small arena and have periodic oscillations with a high level of noise. And he'd been working on that for a while, and they had analyzed hundreds of trajectories of these cells. So each of these blue line is the trajectory of the cell nucleus on this arena, so the X variable. And they had inferred models, and we started discussing, and after a while, we decided to develop this underdamped inference method that with just a single trajectory was able to reconstruct models with the same accuracy as they did before with 400 trajectories. So with one trajectory now, we can get a single cell model that quantifies its dynamics. So that allows to do phenotypic and genotypic correlations between the parameters of the cell and the parameters of the model and the cell behavior. We've also been applying it to higher dimensional problems with several cells in the same system. So that's using just the same data sets, but looking at the places where there were actually two cells in the same arena. And so now we have this kind of random dance of cells that interact. And the really interesting thing is that if you look at an inferred model for healthy epithelial cells or for cancer cells, then just having a look at it, it doesn't look so different. But if we look at the learned model that we get, the parameters are actually very different. So what David did is he was able to reduce the dimensionality of this high complex problem into a two parameters model with a strength of friction between these cells, so the cells slow down when they get close by each other, and a strength of attraction, of interaction between them, so whether they attract or repel at a distance. So what he showed is that healthy cells are actually repulsive. They just bump into each other and turn around, and they have friction, so they slow down on the approach of each other. In contrast, if you look at cancer cells, these cancer cells actually accelerate when getting close to each other due to attractive interactions and an anti-friction mechanism that makes them go faster if there's a speed difference between them. And that allows them to slide past each other more efficiently, and that could be a mechanism for cancer invasion and metastasis. To conclude, we've been developing sets of algorithms to do more with data, to learn models and from data in a robust and efficient manner. It's useful if you have, it's useful as a generic way to infer a model from trajectories. If you know the type of model you want to learn, then it's an efficient way of learning the parameters. But due to extra model selection methods that we're implementing inside it, it can be also useful to use a large class of fin functions and let models emerge and basically get surprised by your data. I'm looking for applications. I'd like to thank my collaborators, Anna Frischman, who worked on the overdamped dynamics with me, David and Chase on the underdamped cases. And I'll finish by thanking my group and my affiliations. So Andonis is working on the field dynamics that I presented. Uray is working on interactions on cells in confinement. And Arthur is going to look at the dynamics of planktonic cells and how they invade marine snow particles. And I'd just like to conclude by saying that we have positions available in the group, and I would like to thank you for your attention.
Any questions?
Her hat. The guy we asked to take the picture took it a bit too quickly. So this is a half an hour walk from the campus in Marseille. So if you're around there, it's definitely worth visiting.
Sorry, I have a question.
Yes.
So you are trying to infer the Langevin equation of the system, basically, the parameters. So there is another approach that I am more familiar with, which is, especially for spatial data, you try to infer the distribution of the, so for instance, imagine that your trajectory is an actual trajectory in space, and you are interested in the spatial distribution of your particles through time, for instance, thinking of animal movement, which is what we study. And I was a little confused that, for instance, in the flocking case, you were showing a realization of the model to see that they qualitatively agree, or, for instance, in the patterns, in the red-blue. Yeah. So I'm thinking how to ask this without sounding like an absolute jerk.
It's okay.
How trustable it is?
I've already made my mind on you.
No. So, for instance, in the next slide is more clear. So you are showing the simulation with the model, and then they learn model, and they look visually very similar. But if I have a stochastic system and I do a different integration of the model, they will look very differently.
Yes.
So my question is whether you are just choosing two cases that look similarly to make the case in the slide, or if you repeat this simulation 10,000 times with both things, how statistically similar they are.
So in that case, we know the ground truth. Yeah. So the interactions that generate these dynamics are actually accurately learned by the inferred model. So here, there's a strong selection bias indeed in this red trajectory, which is that I chose one that turned in approximately the same direction as the previous one, so that it fitted on the same three-dimensional view. Aside from that, if you run this simulation many times, sometimes a few of particles will escape because they will overcome some kind of effective potential barrier and run away. But that's also the case with the green model. But it will always look pretty similar.
So if you run the green model 10,000 times and the red model 10,000 times and you check for actual statistical similarity, that's, I mean, you get...
It's going to be close,
okay.
Yes. It's going to be close and within the error that we've inferred from that we've estimated self-consistently, which is, I think, in this case, about 95% accuracy. So, okay, I can complement this a little bit, which is that here I'm cheating. Why am I cheating? I'm cheating because I know all the terms of the model that I generated, that I used to generate the data, and I'm putting them all, not the same functions, but the same type of terms in the learned model. So here there's self-propulsion, there's alignment, and there's radial interactions. Now, if I forgot one of these, because I didn't know or didn't think about it, then actually I would not be able to capture that. And more problematic is it's very, very hard to check that you haven't forgotten anything, because the space of things that you could forget is too big. So for that, basically visual inspection and a posteriori statistical tests such as correlation functions are a good sanity check for the methods. It's hard, I mean, this does extremely well about capturing things that we know are there. It's much harder to be confident that you've captured everything that could be there. More questions? Yeah.
So in the test you showed where you use the midpoint to infer the coefficients, you mentioned at some point that it is easier to estimate the diffusion coefficient than, oh, I mean, it requires you to have an estimator for D, and you said that it is easier?
Yeah.
And why is that the case?
Okay, so that's actually an excellent question, because it's not that much easier. It depends on the parameter regime you're in. The number one element of answer is that if I look at an individual time increment, then you're looking at the magnitude, at the error you make on estimating force and diffusion using the Kramers-Moyal coefficients, which is the most basic estimators. Then for the force coefficients, then for the force, you get a relative error, which is diverging, or the delta t to the minus 1/2. So it's a high noise problem. Well, if you look at delta x squared over 2 delta t, this is actually the diffusion matrix plus something of order 1. A reason for that is that basically the noise cannot be very high, because on the left and on the right, you have positive definite matrices. And so if you're averaging positive numbers, then the fluctuations cannot be very large. So that's with perfect signal. For perfect signal, it's much easier with small delta t to learn the diffusion coefficient. With noise, if you start adding noise, basically, if I look at delta x squared as a function of delta t, with perfect data, what you have is this, something linear, and then the force starts kicking in. So here there's only diffusion, there's only information about the diffusion, and only in the long run there's starting to have emergent information about the force. With imperfect data, if you add noise on that, then actually delta x squared becomes pretty nasty, You square the noise. But there's a trick. Basically, what you get is something like that, where this is the noise amplitude. But if you use not just this, which is delta x squared over 2 delta t, which is highly noisy, but rather this, which is a 3-point estimator that uses the difference between the first and the second point in this graph, then this gets back to 2D. And so this filters out the measurement noise. So essentially, you can get pretty accurate diffusion estimators, even if you have a high measurement noise, provided that delta t is small. If you have high noise and high delta t, then it's a nightmare, and I have no idea.
Sometimes in movement, people talk about processes which are well described by stochastic differential equations, where the noise has power law behavior, things like that, which I think would make this thing much harder, right? Because you cannot estimate an actual variance, possibly. Is there any...
So you're thinking of Levy processes?
Yeah, exactly.
Yes.
So what would the hope be in that situation? Do you have...
It's not a problem I have thought deeply about, I would say. There's enough systems for which this type of description is actually good enough. And I'm mostly focusing on these systems. These fractional Brownian motion and other Levy flight problems come with their own set of problems, let's say. Honestly, learning this type of subtle dynamics with measurement noise and finite delta t sounds like a very difficult problem. Yeah. Sorry for not giving a satisfactory answer to that.
This one does not require that delta t is constant, right? So for instance, if you have a trajectory where you are missing data for 3 days and then you have data back,
yeah.
Or the sampling is not, because for instance, all the data we have has that problem.
What requires delta t to be constant is the GitHub implementation, because you would need to be very careful if you had a non-constant delta t. What actually you could do is segment your trajectory and drop the few points that are missing when there's a longer delta t. But yeah, there's nothing fundamental except my laziness here to apply this to non-fixed delta t. Also, microscopes have a fixed delta t, and that's my main goal.
Yeah, I was thinking on GPS.
Yes, I understand.
You know everything about f of x, and you know everything about d of x. What did you learn about the living system?
Ooh, that's a pretty broad question. But
one living system where you learn something.
Yes, well, that I can do. That one, for instance, I've been able from the data to learn a force on diffusion fields that we distillated into a physically interpretable model by identifying the terms, by starting with a pretty broad basis of functions and dropping the terms that were unimportant in a principled way. And at the end, well, there's a trade-off between complexity and accuracy. So here we went a bit further towards the simplicity term, so that we had a model that is intelligible into single cell migration, pair interactions that comes as central forces, and pair interactions that comes as friction. So that's what we got out of it. From that, now we have a model. We can use it to change the type of cell, change the size of the environment, change the genetically modify the cells to understand how these simple parameters encode the complex biology that is behind it. So it's a way of quantifying, a way of extrapolating, a way of becoming predictive from initial incomplete data, I would say. And mostly a way of identifying mechanisms that can then be simplified.
So for equilibrium systems, if you have the functional form of the energy function, but not the coefficients, you can use the fluctuation dissipation theorem to get the coefficients, right? So this will give you essentially the forces that you're looking for, right? So in the flocking example, you knew as well the functional form because you knew the kinds of terms that you needed, but you didn't have the, I mean, actually you had because you did the simulations, but in principle, you do not have the coefficients. But at the same time, you do not have fluctuation dissipation theorem there. So how does this compare? I mean, how the two methods compare?
So fluctuation dissipation is a linearization of the dynamics. It's low. Maybe, no, that's not the route I want to go towards. Actually, if you look at this formula, one reason why I love this formula is because it kills the measurement noise, but also it lets two very different terms emerge. This guy in red is odd under time reversal because the delta x over delta t is symmetric with respect to the fit function. And so if you time reverse your trajectory, this guy will change sign. This guy, on the other hand, is even under time reversal. So if you have an equilibrium system, you know that the probability of a forward trajectory and the probability of a backward trajectory is the same. It's reversibility. So that means that in an equilibrium system, there's no such term. This is 0. And this guy is capturing the whole force field. What is it doing? Actually, this is a gradient of the fit functions, and so essentially it comes from the gradient of a potential. So the method separates the two terms, and if you started with equilibrium systems, you would get only that. That term actually does not use the time ordering of the dynamics. This just captures the probability distribution function and infers a potential that is compatible with an equilibrium potential that is compatible with that. This one uses the time ordering to add the out of equilibrium part of the dynamics.
Nice, thank you. And one last question about the phase diagram predictions between healthy and cancer cells. The error in the measurement of the position of the nucleus, is it relevant there?
Yeah. Well, it's not just a measurement error here, it's a definition error. The nucleus is not a point object. So that error is actually very relevant. These are real trajectories. And the measurement noise is actually significant given that we're using a second order dynamics to model it. And so you need to differentiate it twice to infer. So the measurement noise gets crazy amplified.
Thank you.
I'm also around in the next 10 days if you want to come around and discuss and have coffee.
But he's in room 114.
Yes.
And he's giving another lecture on Wednesday, 4 p.m., third floor, Aula 3, on Jersey's inequality.
And if you don't know anything about Jasinski's equality, then that's for you. If you know everything about it, then don't bother coming. It's a broad introduction, not a technical discussion.
Especially like me, it's thank you very much, Pierre. It was great. Yeah, until the 18th, feel free to talk to him.
I don't know how to turn.